Electromagnetic wave lesson. The first thing that I want to tell you is about Ampere's circuital law. You should know that Ampere's circuital law states that integration of B dot dl is equal to mu naught into I, where mu naught stands for permeability in a magnetic field. Okay, so that's about mu naught times I. Magnetic field is B, dl is the length of the wire, and integration of B dot dl is equal to mu naught into I. This is Ampere's circuital law, and Maxwell noticed an inconsistency in this Ampere's circuital law. He just took two parallel plate capacitors and he connected it to a battery and a key. The moment he closed the key, and he connected an ammeter here, okay? The moment he closed the key, the current starts flowing, and you all know that there is a conduction current which is flowing through the wire. Between the plates of these capacitors, there is no connecting wire. So then ideally there's no conduction current here. There's no conduction current here because there's no wire. So but the ammeter still showed the same current IC which went up as down. What is coming out is also IC. How is it possible? Which means there should have been a current here. Okay, first is Maxwell noticed that there is a discrepancy or an inconsistency in Ampere's circuital law, for which he took two closed loops such as C1, which is covering the wire, and C2, which doesn't cover the wire, which is between the plates of the capacitor. And he did Ampere's circuital law for this C1 and C2. Integration of B dot dl for a closed loop C1 is mu naught into IC because the conduction current is there. Whereas integration of B dot dl for a closed loop C2 turns out to be 0 because there is no conduction current. So this is the discrepancy or inconsistency that Maxwell observed, and he said that it's not possible for the current to be 0. There should have been, because there is a ammeter reading which still exists. The ID and IC there has to be a current which flows between the plates of the capacitor, and he tries to justify what is that current. Okay, because so then looking at this, he says that as the capacitor is getting charged, as the battery is switched on, the capacitor is getting charged, there will be an flux, electric flux, which keeps on increasing, which is d phi E by dt. The electric flux is increasing with time, which is known as d phi E by dt. As the flux is increasing, that is the rate of flux, electric flux is increasing. You all should know the rate of electric flux. This is known as time varying electric field, or time varying electric flux results in a time varying magnetic flux, which results in an induced current known as displacement current, which is getting induced between the plates of the capacitor. So that's known as the displacement current, and this displacement current is directly proportional to d phi E by dt, the electric flux. So ID is equal to epsilon naught into d phi E by dt, where epsilon naught is the permittivity, and it's a constant here. So then what is the root cause of displacement current? Is the varying flux, electric flux between the plates of the capacitor. Correct? So then that's what it is. And what is the displacement current? It's that current which flows between the plates of the capacitor when there is a varying electric field, or varying electric flux rather. And thus he modifies the Ampere's circuital law to be integration of B dot dl. Integration of B dot dl is not only mu naught into IC, but it's also mu naught into ID, considering IC and ID are two currents which are flowing here. So then mu naught into IC plus mu naught into ID itself is epsilon naught into d phi E by dt. So thus this is known as Maxwell's modified equation, or Maxwell's Ampere's circuital equation, however you want to call it. This is what it is. Okay, so then there's also one more thing you should know, that IC should be equal to ID, and because the current is continuous, I is continuous. The continuous means the ammeter always shows one particular current which goes here, and therefore IC should be equal to ID. So let's come to next thing. Okay, one second, hold on. Now let me show you how to show that ID is equal to IC by derivation. You know that ID is equal to epsilon naught into d phi by dt. But you know flux itself is q by epsilon naught from the first lesson. You plug it in there, epsilon naught into d by dt of q by epsilon naught cancel, dq by dt is simply conduction current. This is the proof to show that id is equal to ic, and therefore the ammeter will always show a current I. That justifies it. Okay, I hope you're clear with this. So next is what are electromagnetic waves? Electromagnetic waves are produced by accelerated charge particle in space. An accelerated charge particle produces a sinusoidally varying electric field and magnetic field, which are vibrating perpendicular to each other and also perpendicular to propagation of the wave. So this graph that I taught you is very important, where the electric field is along y-axis, the magnetic field vibration is in blue color, which is along the z-axis, the propagation of the wave is happening along x-axis, and the maximum EMF, maximum amplitude is known as E naught, and the maximum magnetic field is known as B naught. It's just a peak value or the maximum amplitude. Okay, and the things that you got to remember here, they will mutually perpendicular to each other. And how to represent electric field is along y-axis, so j cap is E naught sin kx minus omega t, where E naught refers to maximum amplitude of EMF, k refers to propagation constant, which is 2 pi by lambda, omega refers to angular velocity 2 pi mu, or angular frequency 2 pi mu. So plugging in 2 pi by lambda and 2 pi by t into these equations, or 2 pi mu, omega is also 2 pi mu. Substituting those here, you can take 2 pi lambda and you get various forms of equations which can be written here. Then the magnetic field, its direction is along z direction, which is k cap. Okay, so bk is equal to b naught sine, same thing can be copied. The next thing that you need to know is c is equal to, the whole lesson you need to mug up certain things such as c is equal to e by b, c is equal to e naught by b naught, c is also 1 by root of epsilon naught into mu naught, where epsilon naught is 8.854 into 10 to the power minus 12, and mu naught itself is 4 pi into 10 to the power minus 7. On plugging in these values in this, you get 3 into 10 to the power 8, which is the velocity of light in vacuum. Supposing if it's going to be in medium, the electromagnetic wave is going to travel in a medium, then the velocity is 1 by root of k times epsilon naught and mu r times mu naught. So V also becomes c by root of k into mu r. Then the properties of electromagnetic wave. You have to mug up all these properties, more to do with memory. Electromagnetic wave are produced by accelerated charge particle, and hope it's recording. Yeah, they do not require any medium to travel. They are produced by time varying electric and magnetic field, which oscillates sinusoidally perpendicular to each other and also perpendicular to propagation of the wave. The electric field and the magnetic field are always in the same phase. The vibrations are in the same phase. That shows, when you draw the graph, they all start in the same phase. There's no phase difference. So that's what is that point. And the speed of the electromagnetic wave in vacuum is c is equal to 1 by epsilon naught into root of epsilon naught to mu naught. The speed of the electromagnetic wave in medium is v is equal to c by root of k into mu r, which together can be called as constant, some eta they've specified. And okay, next is the very important point is energy, about energy density. This is the point that you have to recall. Okay, the electromagnetic wave carry energy. And we are going to talk about energy density of an electromagnetic wave, EM wave. It has got magnetic energy as well as electrical energy. E is electrical energy, magnetic energy is ME. Electrical energy is the energy stored by the capacitor, and you have to mug it up half into epsilon naught into capital E square. Okay, which came from half CV square, which is the energy of the capacitor, but C itself is epsilon naught into A by D, and V itself is E into D, so E square into D square, D and D get cancelled, A and D can be brought down to convert into energy density, so half into epsilon naught into E square. Okay, this is D and half. Okay, so then that's what it is. So let's otherwise mug it up, half into epsilon T square. And the magnetic energy is half into B square by mu naught. You should know this. But in this, E is not E, E is E RMS square. And B is also B RMS square. Okay. So then C can also be E by B. C can also be E RMS by B RMS. C can also be E naught by B naught. And given that, we're going to find the total energy density. The total energy density, U total density, is equal to half into epsilon naught into E RMS square plus half into B RMS square by mu naught. But you know C is equal to E RMS by B RMS. C is equal to E by B. So B RMS can be written as E RMS by C. Substituting this value in B square, this will become half into E RMS square by C square into epsilon naught. This alone, correct? Because B RMS is epsilon E RMS by C, so square it. You know C square itself is 1 by mu naught into epsilon naught. So mu naught get cancelled, the epsilon naught goes up. Half into epsilon naught into E RMS square. And this is also half into epsilon naught into E RMS square. Therefore, put together it will be epsilon naught into E RMS square. That's the formula. This is the total energy density formula. You can mug it up. The total energy density formula is epsilon naught into E RMS square. Okay, but you know that E RMS is E naught by root 2. On plugging this in, it will be half into epsilon naught into E naught square. So you don't have to know this derivation. Nobody is going to ask you for this derivation ever. The total energy density of an electromagnetic wave is epsilon naught into E RMS square. The total energy density of an electromagnetic wave can also be half into epsilon naught into E naught square. As long as you can memorize both of this formula, you don't need the derivation, but if you can do the derivation, nothing like it, okay? So then that completes the energy density, okay? Next is about momentum. Next property is electromagnetic wave carry momentum, and which I told you energy is equal to Pc, and so the momentum is energy by C. Not energy density. Energy itself is Pc, so momentum P is equal to U by C. So that's one thing, very nice. And so then the electromagnetic wave next properties can be just memorized. Electromagnetic waves are not deflected by electric and magnetic field. Then they obey the principle of superposition, reflection, refraction, polarization, diffraction, interference. And these are all the properties of electromagnetic wave. And the most important question that comes is, they carry energy. So they get heated up, they get dried up because it absorbs the energy, heat energy. So that shows it carries energy. How do you prove it carries momentum? We cannot prove that, because when you show your hand against the sun, the rays are coming and hitting your hand, the hand get heated up, but his hand is not moving even though the particles of the rays are moving, because the electromagnetic wave consists of electrons or any charged particle whose mass is very negligible. Mass is less, velocity is more, but here hand mass is more, the velocity is negligible, so approaches zero, so the hand does not move. So really you don't feel the transfer of momentum, you only feel the transfer of energy, but definitely carries energy and momentum. So let's go to the rest to solve the numericals. So it's all straightforward. You can understand from these questions how I've done the numericals. If you don't know any specific numericals, you can come back and ask me doubts. So this is all the lesson is, and then the tabular column, which is very, very important. So the numerical part of it, if you don't understand, you can always come back to me and ask me which numerical you don't get it. The next thing that I want to teach you is, like, first thing is this tabular column. If you don't know this tabular column, you're gone. In this whole lesson is about this tabular column. The first wave, first I'm giving you a clue to remember this lesson. What is it? I am sitting here with a radio next to me, which is a radio next to me, and a microwave next to me. I'm carrying a small scale, which is a 10 centimeter scale. Just remember that it's a 10 centimeter scale. I'm talking about a radio, I'm talking about a microwave, I'm talking about a 10 centimeter scale, I'm talking about an aircraft. I'm hearing an aircraft which is navigating on the, when I'm heating something on the microwave, I'm also hearing an aircraft flying. Then I'm taking the remote and I'm switching on the television. When I'm putting a PC Sriram's photography movie, which is fog photographies, like a movie like Roja is what I'm watching. So this is the basic thing. where I'm having a small scale, which is a 10 centimeter scale. Then I'm having a radio, I'm having a microwave oven, I'm heating something on the microwave and I'm eating on that. At that point of time, I'm also hearing an aircraft flying outside, and at that time I'm taking a remote and I'm watching a Mani Ratnam movie in which there is a PC Sriram picture, which is a fog photography. All this will lead me to this tabular column, in which the first thing I'm talking about a radio wave. Radio wave is the longest wave. You know, you get to hear radio or television because the signals go to the satellite and comes back, which shows its longest wavelength. Next is microwave. Radio wave, microwave, then infrared wave. I told you about remote. Remote works on infrared. Then is visible light. Then is ultraviolet. Between infrared and ultraviolet, there will be visible. So then infrared, visible light, ultraviolet rays, X-rays and gamma rays. That's all. These are the various kind of rays, and the lambda is the longest. So it's greater than 10 centimeter. The scale that I have, the plastic scale is 10 centimeter, greater than 10 centimeter. Microwave is from 10 centimeter to 1 millimeter, the smallest unit of that scale. Infrared is 1 millimeter to 700 nanometer. 700 nanometer. Visible light is 700 nanometer to 400 nanometer. Ultraviolet is 400 nanometer to 1 nanometer. Then X-ray is 1 nanometer to 10 to the power minus 3 nanometer. And then gamma ray is lesser than 10 to the power minus 3 nanometer. So the longest wavelength to shortest wavelength. This is in the form of longest to shortest, which is in descending order, decreasing order. So frequency will be obviously increasing order, correct? The frequency will obviously be, okay, let's write, mug it up, 10 to the power 4 to 10 to the power 8 hertz, 10 to the power 8 to 10 to the power 14 hertz, 10 to the power 10 to the power 8 to 10 to the power 12 hertz, 4 gap, okay, 10 to the power 12 hertz, then 10 to the power 11, little overlapping with 10 to the power 14 hertz. Then it's 4 into 10 to the power 14. This 4 comes beginning and 7 comes later. 7 into 10 to the power 14 hertz. So then next is, I'm telling you to remember like this. U refers to you students whose age group is 10 to the power 16 to 10 to the power 17. X-rays, X includes you guys as well as my X students. So 10 to the power 16 to 10 to the power 18 X students is age. Gamma rays completely passed out students who are gone, who like 10 to the power 18 or 10 to the power 19 to 10 to the power 22 or 10 to the power 18 to 10 to the power 22, whatever it is. That's about the frequency in hertz. And the frequency is in the form of, this is descending, this is ascending frequency. It's going on increasing, ascending frequency. Next is source. What produces radio wave is a accelerated charge particle in oscillating circuit. Oscillating circuit le accelerated charge particle. You know, the entire lesson electromagnetic wave is based on accelerated charge particle, correct? So microwave are produced by vacuum tubes. Vacuum tubes such as klystron or magnetron are the two vacuum tubes. Next is infrared rays are produced by hot bodies. You know, red hot, that shows that hot bodies produces infrared rays. Visible light are produced by incandescent lamp. Any lamp produces visible light. Ultraviolet rays are produced by sun. X-rays are produced by fast moving electron when gets stopped by a lead. When gets stopped by a metal like lead. Metal such as lead produces X-rays. Gamma rays are produced by radioactive decay. Please write this tabular column twice and become clear. Next is application. First one, radio wave. The application is obviously radio communication. Television, radio. They're all based on radio wave. Second one is microwave. Microwave is used in remote sensing. Basically, which is nothing but aircraft navigation. I told you when I was eating a sandwich, I heard an aircraft. So microwave le heat panni saapidumbodu aircraft navigation ku or remote sensing ku microwave is useful. Other than that, microwave is also useful in cooking. So these are the uses of microwave. Let's go to infrared ray. You know, remote. I took the remote and switched on. So a remote control, remote sensing is different. Remote control works on infrared rays. Also infrared rays, I'm switching on Maniratnam movie in which there's a PC Sriram photography, which is basically a fog photography. Fog photography or night vision camera, these are all the applications of infrared ray. Let's go to visible light. Fourth one is visible light. You know, visible light gives us visibility and is also useful in carrying out some chemical reaction. Some chemical reaction you can show light and you can carry out. So next, fifth one is ultraviolet. You know, ultraviolet ray, you would remember that it's a disinfectant. Just don't forget, it's a disinfectant. Okay, swimming pool cleaning, water cleaning and all, ultraviolet ray is useful. Other than that, I told you to remember Leonardo DiCaprio, that movie Catch Me If You Can, in which he forged documents will be identified by him. Forensic science also is based on forensic science, also ultraviolet ray is useful. So these are the applications of ultraviolet ray. Sixth one is X-ray. X-rays are used in bone crack, building crack. Okay, apart from that, you should know that for an atomic study or a crystal study, X-ray is what is useful. In the class, I would have mistakenly said that UV radiation. No. X-rays is what is used in atomic structure or crystal study. I hope you are clear. So X-ray is done. Next is gamma radiation. What about gamma radiation? What is the use of gamma radiation? Gamma radiation is used in cancer treatment. And also gamma radiation is used, it's nuclear decay, right? So nuclear study. So these are the applications. You must by heart this tabular column. Once you do that, you'll be able to answer any question that comes your way and the lesson is over. Only the numerical part of it is pending. I'm sure if you go through the numerical, if you have any doubts, we can always discuss in the class. See you guys.